Okay, so if our two speakers would come on camera for a minute. Now, let me introduce first Trevor Lanting. Trevor leads D-Wave's product development organization, which includes teams responsible for software, systems, and cloud services. Trevor has helped drive the development and deployment of 5 generations of our annealing quantum computing systems and specializes in connecting fundamental research results and insights with real-world applications, focusing on harnessing quantum mechanics to produce fundamentally new computational capabilities. Trevor holds a BSc in physics and astronomy from the University of British Columbia and a PhD in physics from the University of California at Berkeley. Murray Thom, who many of you probably have seen or met before, is Vice President of Quantum Technology Evangelism at D-Wave, and he has more than 20 years of experience in the quantum computing industry. He's the globally recognized speaker and thought leader and helps businesses and organizations around the world understand quantum computing and the transformational impact it can have for them today. On previous roles at D-Wave, Murray was responsible for the development and delivery of the Leap Quantum Cloud Service and the Ocean open source tools. He's also led teams engaged in customer projects related to applications, algorithms, and performance testing. He also likes to let everyone know that he even assembled a few early quantum computers by hand. So with that, we'll get started and Trevor will kick us off.
Great. Thanks, Susan. And thanks to everyone who's joining today. We really appreciate the time and the opportunity to give you a deeper dive into what we're working on. So both Murray and I are sitting here in our Burnaby office. This is the bulk of our development teams are sort of situated in Burnaby. There's our data center and our R&D center is about 50 feet in that direction from where I'm sitting right now. And it houses several of our annealing quantum computing systems, including the QPUs that we're going to be actually running live demos on today, which is very exciting. Today, we want to spend a few minutes doing a deeper dive on the fast anneal feature, which is a new feature that we released in April of this year. Murray, if you go to the next slide, please. So on the 17th of April, we made this feature generally available on all of our QPU solvers. So what is fast anneal? What at its core, it gives users the capability to do annealing protocols on timescales that are faster than the timescales for the chip or the qubits to exchange energy with their environment. So really, this feature is giving users access to coherent quantum annealing at scale on all of our QPUs that are currently deployed in Leap. So really, this is the core capability that's been underpinning a lot of the basic R&D work we've been doing over the last 2 years, including the simulation work, including some work I'll talk about in terms of a scaling advantage that we've seen over classical approaches to solving hard spin glass problems. And more recently, it's the core protocol that underpinned what we believe is a demonstration of computational supremacy. So the plot, and Murray will get into this in a lot more details in the demo that we're going to walk through, but one of the papers that we published in 2022, where we really showed coherent quantum annealing at scale with this protocol, this is one of the figures from that paper. So the experiment itself is very simple. We're taking a one-dimensional linear chain with some couplings between some standard uniform couplings between the qubits, and then we're rapidly performing quantum annealing on that chain. So there is a theoretical prediction for how many kinks form in that chain. The ground state of that system is very, very simple. Is all the qubits either aligned or pointing in one direction or the other if it's a ferromagnetic coupling, or as every neighbor is pointing in opposite directions if it's an antiferromagnetic coupling. So the ground state, this is not at a core a hard problem in terms of finding the ground state configuration. But there is a theory called the Kibble-Zurich model that describes a coherent system undergoing this fast rapid anneal in terms of how many kinks form in that chain. And we'll get into the details and Murray will actually run the experiment. But what you can see in this plot is the kink density of this experiment for some of these chains for this experiment run at various temperatures and the different colors of the different temperatures of the QPU as a function of this fast anneal time. So how rapidly you were actually running the annealing protocol. And you can see for very, very fast anneal times on the scales of tens of nanoseconds to up to about 100 nanoseconds, that the behavior of the QPU exactly aligns with the predictions from coherent theory. You can see, though, that for longer timescales beyond about a few hundred nanoseconds, you start seeing a peeling away. So this kink density actually doesn't continue to fall, that you're seeing in basically what we're calling anti-Kibble-Zurich behavior. And this is temperature dependent. And this really is the regime, the timescale in which the QPU is able to start exchanging energy with a thermal bath with this environment. But really what we've identified in this paper was that there is and with this work, is a regime where the QPU can undergo quantum annealing without exchanging energy with this environment, this coherent regime. Really putting this feature in the hands of all of our users really gives all of you the chance to build applications that leverage quantum supremacy, really allows users to develop increasingly sophisticated quantum simulations and demonstrations of simulating actual real systems. And it really allows researchers a tool to explore the role of coherent dynamics in driving the core computational performance of this technology. So we're really excited about it, the feature, and it's been in the hands, like I said, of users. We released it in the middle of April. Murray, if you go to the next slide, please. And the uptake and the response from the market has been really gratifying, sort of exceeded my expectations for how quickly people would really dig into and get their hands on this technology. Really, and it speaks to the kind of the power of our ability to put new technology nodes and new features into the hands of users as quickly as we can. The Fast Anneal feature over the last 3 months has seen close to 2.5 million customer jobs that have been submitted to the Leap Cloud platform that use this feature. In addition, we've had 2 Advantage2 prototype chips. So these are smaller scale versions of our eventual Advantage2 product have been in Leap for the last couple of years. And we've seen what is approaching 10 million customer jobs submitted to these 2 Advantage2 prototypes. So well over 8.5 million. And really, this speaks again to the growing power of the Leap Cloud platform. The fact that all you need is an internet connection to access these technologies. I'll talk to you in a couple of minutes how to sign up for Leap. But really, as soon as we make new technologies, new chips, new protocols, as soon as we develop them, we can make them available in Leap and roll them out very, very quickly. And this really is going to allow us to accelerate the capabilities of this technology. Next slide, please, Murray. I want to talk a little bit about a paper that used the Fast Anneal protocol that really sort of showed that what I talked about a minute ago, this real core scaling advantage of quantum annealing over classical approaches. So this paper was published in Nature last summer in mid-2023. And the core part of this paper, the core data from this paper is shown in the plot on the right. So this is really taking 3D cubic spin glass problems, and these are known to be, computationally intractable at scale, are very, very difficult to find low energy configurations of these spin glasses. And what we're showing in the plot, again, is very similar to what I showed with the Kibble-Zurich experiment. We're showing residual energy per spin. You can think of this as just a distance away from the ground state. So lower is better and lower is lower energy as a function of anneal time. And shown in the blue is data from annealing quantum computing systems, one of our Advantage QPUs, compared to some standard classical heuristics for solving these problems, both simulated quantum annealing shown in the teal and simulated annealing shown in the orange. So the key thing that I want to get across here is this difference in slope. So there is a scaling advantage where we're able to burn down to lower energy, better solutions, lower energy configurations much faster with annealing quantum computing systems versus these classical heuristics. For very fast anneal times, also the QPU, the annealing systems are tracking exactly as you'd expect based on coherent quantum theory. And so this really is really a good attestation to the connection between coherence and the core computational performance, the core computational resource that we're harnessing with our technology. Next slide, please. So the success of the Fast Anneal feature, a lot of what we learned when we developed it have really inspired sort of a roadmap for next generation of QPU controls. So we were able to actually recently enhance the Fast Anneal protocol internally in our R&D facility to basically show that some fundamentally new capabilities and controls for a QPU. In particular, we've been able to use ancilla devices in the fabric of our larger scale annealing processors to do in situ preparation of excited states. We've also been able to develop a qubit readout that reads out in an arbitrary basis, and not just the spin basis, but superposition basis, like the energy basis. And really, this allows us to do direct in situ probes of quantum dynamics. And like really excitingly, and this is something that we talked a little bit about at qubits, we were able to show a violation of something called a Bell's inequality in the fabric of our annealing QPUs. So this is physicists will sort of know what Bell's theorem is, but at the core, Bell's theorem really is a theorem that describes the statistics that you should get out of quantum systems versus classical systems, and at the core was a key sort of a key plank in the overall establishment of quantum mechanics as the fundamental theory of what governs our world around us. And if you can show a Bell inequality in the fabric of a processor or in other physics experiments, that's a key signal, or basically a key sign that quantum mechanics is really dominating and driving the behavior of your system. Going forward, we expect that these next generation controls are going to allow users to perform much expanded and richer quantum simulations. And so we're quite excited to continue development of these features. Next slide, please. So I want to also just emphasize that all of the technology in terms of the Fast Anneal protocol, the Advantage2 prototypes, they are available through APIs that you can access today. You can sign up for the Leap cloud service. We offer some small amount of time on our systems for free to anyone who signs up to the Leap cloud service. And so you can run all of the demos that we have in Leap, and as well as the demo that Murray is going to show in a couple of minutes. And it's very easy. You just need an internet connection, and you can sign up for Leap. Next slide, please. So this is a screenshot with the code examples that you'll see when you go to the resources page in Leap. And I want to again emphasize that all of this you can run at any point. It's very easy to run. And Murray is actually going to walk you through a demonstration of the Kibble-Zurich experiment. And I think I'll probably turn the floor over to Murray next. So one more slide, I think, before doing that. There's you can do an even deeper dive into the Fast Anneal protocol and learn a little bit more about it. If you're interested, we have a white paper that we made available recently. So, in the QR code here, we'll link to the white paper. This is also available on our webpage. All right. So I'm going to stop talking, and we're actually going to see the system in action. Murray, take it away.
Right on. Okay, I'm super excited. This is definitely like a favorite feature and topic for me, and I'm also stoked. We've got, more than 100 people here. So I'm going to be talking to you about some things that I would say is not broadly understood, even in the quantum computing community. And so this is like, secret, close the doors here. You're all going to get like a deep window into quantum computing and what its capabilities are and what makes it faster. When my kids were little and we were waiting at the bus stop, we used to play a little game to pass the time, which was red light, green light. They would stand about like 30 feet away from me, and then I would turn my back and say green light, and they would all start running, and then I would say red light, and then they'd have to freeze, and I'd turn around and see if I could see them moving, kind of thing, right? But I'd stop them mid-race. The thing about quantum mechanics, when we want to harness it to do work for us by computation, is that it's so fast that by the time you say red light is already at you. It's already won the game, right? Fast anneal is what's allowing us to catch the quantum mechanics in the act and see what's happening, and particularly coherent quantum dynamics. And when I say coherent, when Trevor and I are talking about coherent, we mean the phase when the quantum computer is operating without any interaction to its environment. So not even like a single photon of light is hitting it. It's just blissfully computing for you without interruption. So yeah, this is what we're going to get to dive into, which is really exciting. And yeah, I'm going to share lots of secrets and lots of things that people don't know yet. So this is going to be lots of fun. And then, yeah, I see also we've got some fantastic questions here as well. So the highlight here is that this is really related to how fast information can get processed, right? How quickly can the universe compute information? Like, what are the speed limits? And that slide that Trevor showed you earlier, quantum computers have a faster speed limit than classical computers, and it's significantly faster. So it doesn't matter if you're using a CPU or a GPU or and FPGA, like central processing units, graphical processing units, they all have the same speed limit. So when Trevor says this is how fast classical compute is, he's talking about every classical computer in all types. And quantum computers can connect more quickly. So we're also talking about Kibble-Zurich, the Kibble-Zurich mechanism and Kibble-Zurich theory. So what I want to relate to you here is that Tom Kibble in the 1970s and 80s was really curious about something. And what he was curious about was that in the Big Bang theory, the universe starts as this really like hot, incredibly dense, ball, pinpoint, I'm not quite sure what, who knows. And then it expands into the universe that we know. And when it's in the ball, like, some sort of plasma or something like that, it's just this really even distribution of extremely hot, energy and matter. But he asked a question, it's kind of like a why is the sky blue question, which is that if it started out uniform, why didn't it end up uniform? Like, why are we not in a universe which is just like an even fog of energy and matter everywhere? Because we know that's not how the universe is. There are empty space areas of the universe, and then there's stars and galaxies and planets, and that indicates structure. So structure is going to be an important part of what I'm going to be talking to you about. And this whole demo I'm going to be sharing with you is the fact that the way and the density of how stars and galaxies emerge in the universe is related to how information gets processed in quantum computers. It's related to how quantum computers are faster than classical computers. And I'm going to show you a demo that's going to allow you to explore that yourself and give you some insights into quantum measurement, insights that I would say nobody in the human race has ever had before, because it's very difficult for us to measure quantum systems. And you now have a tool that in just minutes, you'll get a chance to like project and measure a quantum system and see how it behaves. So yeah, I hope we're all excited for that. This is going to be great. So, all right. So Tom Kibble came up with this theory for how the density of stars and galaxies emerge in the universe. And Wojciech Zurek, who was also doing research at Los Alamos in the 1980s, realized that actually relates, that same theory relates to quantum systems. And what we're going to be exploring today is that it's also how quantum computers, how information sort of gets processed and materializes in quantum computers. So, a quantum computer is just a device that uses quantum effects to accelerate calculations. And there are different ways to use those quantum effects as a resource for a computer. In the gate model systems that we're building at D-Wave, the quantum effects are to allow the computer to store more information, which is very powerful. In the annealing systems that we're building, the quantum effects are to help us move between solutions more quickly. So we have an exploration phase, which is when we're moving through solutions, which is kind of like our superposition phase. So think about that like everything is very even, right? It's evenly distributed. And then we've got like the measurement phase where we're basically honing in on a high quality solution. And that's where the structure of the answer, the information, the ones and zeros occurs out of the quantum processor. So those are the two scientists, Tom Kibble and Wojciech Zurek, and the Kibble-Zurek mechanism that came up with this theory that really relates to things at like the universal scale and also at the microscopic quantum scale. Woo, fascinating. All right, so I'm going to switch over to the demo screen now. And yeah, keep the questions coming in. So as Trevor mentioned, if you just search D-Wave Leap, any of the top links that come up will take you to our Leap platform. And if you already have a Leap account, you can actually like log in and follow along with what I'm doing. And if you're watching the video later, you can pause it as you're kind of going through steps. I've already logged in and created an account. So this is the Leap dashboard here. And we're going to be looking at the Explore Your Examples section. And when you click on Explore Your Examples, you're going to see our code examples and notebooks. And it just so happens that the demo is right here, but that's because of the date in which we're doing it. If you want to search for it, you just search, fast for fast Anneal or Kibble-Zurich, and this will pop up. And then you can click it and you can look at the README from the demo. So one of the things I was just explaining to a colleague recently was about annealing. What does annealing mean? The origins from that come from metallurgy, right? You have a lump of metal and you want to change its shape into a tool that you can use. And it's very hard, so you can't do that at room temperature. So you heat it up until it becomes soft enough that you can change its shape. And then you hammer it into position. And then an interesting thing happens. When you cool it down, depending on how quickly you cool it, its properties change. If you cool it very, very slowly, it remains soft. And so if you want to make wire out of it and draw it into like wire, that's useful for you. If you cool it very, very quickly, it's hard. And so if you want to make kitchen knives and things like that, that's useful to you. So depending on the properties of what you want to have out of it, changing the rate with which you cool it changes its properties. And if we're going to understand why that's the case, we kind of have to understand like what's actually happening in the material. And the interesting thing is that when you anneal it slowly, it's actually relieving stress inside the material, and that relief of stress is actually making it softer, physically softer. It also means that it has better electrical conductivity and other things. And when you cool it really quickly, you keep a lot of stress, and that internal stress is what makes it hard. So that turns out to be very important for us in terms of using quantum computers for calculations and applications, and I'm going to talk to you a little bit about that. But really, this relates to, we can relate this to like materials that we use in our daily lives, like water and ice. Those are made up of exactly the same molecules, but they're just in a different form because they're in a different phase. And how we use it, you know, you swim in water, you skate on ice, right? That has a very big impact in terms of those phases. With metal, you can have metal that's non-magnetic, and you can have magnetic metal, right? If it's non-magnetic, you can use it for whatever you're using metals for, scissors maybe. And if it's magnetic, then it can keep, you know, photos on your refrigerator. So how we engineer and use our tools based on their phases of matter is important. And we can use quantum computers to learn things about the phases of matter in order to design them and use them for specific purposes. So we're going to be talking a little bit about changes of phase. And we're also going to be talking about topological defects. And I mentioned this earlier, the Big Bang, very hot, very uniform, everything's sort of even all the way through it in the early stage. And then later we actually have structures in the universe. And so we're not going to study something as complicated as the universe. As Trevor mentioned, we're going to look at just a ring of things that are up or down. And that's intended to be simple because then it's really easy to see by eye what what we're looking at, what the quality of the solution is. So let me propose a game to you all. Let's imagine that I was going to hand you a deck of cards that's completely mixed up. And I don't just mean it's shuffled. I mean that the cards are kind of face up and face down, like they've tumbled on the ground and just been gathered together. Now imagine I was going to give you a task and basically ask you to lay the cards out on the table one after another in a line. And the task for you is that in the line, make sure that the card is matching face up or face down with the cards next to it. Okay, so the first card you put down, it's face down. After that, you want to keep flipping the cards so that they're all face down. That's probably pretty easy as a task goes. But if I rush you, you may accidentally put a card that's face up. And at that point, you should keep putting them face up. You made a mistake in the past. If you try to flip it face down, you'll have made 2 violations instead of just 1. So you keep it face up, and then accidentally, if you put one face down, you're going to keep it at that point. So you're going to end up with these long sequences of things aligned in one direction or another. And if I make you do it really, really fast, you'll have more of these kinks, these places where the cards are not in alignment. And that's what this diagram is kind of showing here. And that's very much like looking at the internal structure of like a material, or in other applications, if instead of thinking about these as like elements in a material, but like part of an optimization problem in business, these states would be like yes, no decisions you'd be making in business, right? Am I going to assign this delivery driver to this delivery? Yes. Am I going to be assigning this, Bob to it? No. Those are decisions that have relationships. If you're in the machine learning community, these are like neurons in a neural network. Are the neurons firing or are they not firing? What patterns are they detecting based on that? And you choose the interconnectivity for that. I'm choosing something very simple here, which is just connected to the ones on either side of it in a line. So here's the idea. If you progress really slowly, you should find the states where all of them are up or all of them are down. And if you go really quickly, if you quench, like in metallurgy, which is what our fast anneal feature is, then you can actually catch it in a circumstance where it still has some of these kinks and it's frustrated. Okay, so one of the great things here is that if you have a GitHub account, you can not only view it in GitHub, you can actually open this demo in a GitHub code space. It takes about a minute for it to open. I've already done that. And it basically deploys a computer in the cloud and sets up a developer environment right in your browser, which I've done right here. I've connected that to Leap, and then I've run this Python app. And the usage here is right here in the README instructions. So I've run the Python app, and then I've said, okay, it said, do you want to open this in another browser window? And I've said yes. And this is the application here. Okay, so here's our demo. There's a lot on the screen here. So I'm going to start with this beautiful diagram of spins here. So here the spins represent the cards, right? And if they're red, then they're face up. If they're blue, then they're face down. So I can zoom in on one of these, right? There's actually, this is sort of showing the superposition of each of the spins is in both states at the same time. try not to be too disorienting. And I mentioned that they're in a line, but obviously we're not looking at one deck of cards here. We're nearly looking at 10 decks of cards, 512 spins. So we've coiled them into a cone, I guess, into a cone, just so that we can see them all in one place. And down here, I've shown you a graph, and this graph is basically showing us, so as I move along horizontally from the left to the right, I'm increasing time for the fast anneal feature, and this is in nanoseconds. A nanosecond is a billionth of a second. So if I was going to count nanoseconds, 1 billion, 2 billion, 3 billion, 4 billion, that's how you count nanoseconds in real time. So these are very, very fast times. We have to get down to these fast times if we're going to catch quantum mechanics when it's coherent and it's not interacting with anything else. And if we slow it down, then it can begin to interact with its environment. And then here on the y-axis, as we go from the top to the bottom, this is the number of kinks. So high kink density means just lots of mistakes, and low kink density means we've got long, long sequences where we've got all the cards face up or face down with one another. So, all right, let's start an experiment here. We're going to do about 10 decks of cards. We're going to keep our coupling strength set where the default is, and I'm going to give it 7 nanoseconds to run. We have multiple quantum computers in the cloud. I'm going to use the new Advantage 2 prototype, and we're going to run this. Everybody ready? It's done. So that's what we mean when we say like a real-time quantum cloud service. We can click a button here and basically get calls to our quantum computers and answers back. And in the time it took to do that, I got 100 answers. And I'm just showing you the best of the 100 answers. So that's how fast this is running, because these computations are happening in nanoseconds. Okay, so this is showing us that in those 7 nanoseconds that we ran here, we have about 0.07 kink density. And I can tell you that means that on average, these lengths of things are about 35 in length. And there's probably about, there's about 35 kinks in this sequence here, which means that the length is somewhere around 14 or something like that. So if we look at this, we can see there's places where it's like, oh, all the faces are down, then the faces are up, then the faces are down, and we can see the places where there's some frustration. So we rushed it so much that the quantum computer wasn't able to get it so that they were kind of more closely aligned. So now I'm going to give it 3 times as much time, up to 20 nanoseconds. We're going to run this again. Okay, so now we can see here on the plot, it's showing us, it's calculating, okay, we gave it 20 nanoseconds. We've got about 0.04. So now the chains are starting to get longer, and we've got a smaller number of kinks in there. We're going to go up to 60 and run this again. Okay, so now we're getting even longer sequences here. And the average length, we're getting closer to 0.02. This is the point where we've got about 4 or 6 kinks in the overall sequence, with lengths on the order of like 80 or 100 of these aligned with one another. You can just see how long this blue ring is, where it's all in alignment. So we're getting a chance to rush the quantum computer and then see how many mistakes it's made. And then if we give it a little bit more time, the number of mistakes is going down rapidly. So when Trevor and I were talking about the speed limit for quantum computing, this white bar, this is the predicted Kibble-Zurich behavior, the speed limit for a coherent quantum computer, and how quickly it's able to remove stress and frustration from its solution, which is actually very analogous to like when you're doing a business optimization, you're removing stress and frustration from your team members in the way that they're doing their grocery deliveries or something like that. Now, I did a LinkedIn post about this, and there's a really fascinating thing I want to mention here, which is that quantum states are famous for being fragile, right? Here we're talking about the phase where the quantum computer is not interacting with its environment at all. But I can actually make this run long enough that I'm actually going to breach this coherent behavior, and it's going to start interacting with its environment. I'm going to take it up to 85 nanoseconds, and we're going to run this again. There we go. We got our answer. And here's the thing. It's outside the bar, but the solution quality is even better. So here's the thing that is not well understood from the whole quantum community. The system is now slow enough. It's had a chance to exchange some photons with its environment, and that has changed the rate with which it's able to improve the solution quality. It's effectively slowed down a little bit. But look at this. We're down in like hundreds of kink density here, right? This goes all the way up to 1.00. At 1.00, there's kinks everywhere. So this is way down low. If the quantum state was destroying the calculation, then this point should come all the way back up to the top, right? When this starts getting measured, it should start destroying the computation. It should go up to the top, and that's not happening. And that's because quantum annealing behaves differently. It just interrupts the process from moving between the solutions. It doesn't destroy the calculation. You are able to still continue to improve the solution. And that's fundamentally not super well understood. And that's why we're getting these really high quality answers from these systems that are, quantum annealing systems that have near-term applications. They're easier to build, and you don't need to know quantum mechanics to program them. I mean, we're definitely dipping into the quantum mechanics here because we're finding out and understanding why it's faster. The theory is showing us that it's provably faster. And then here we are, we're measuring things ourselves, and we're matching them to the theory to say, hey, yeah, in fact, the system behaves exactly the way that the theory tells us it should behave here. So it's fascinating. We're looking at quantum measurement. We're getting a chance to explore quantum measurement in a way that the original quantum physicists who pioneered the theory didn't get a chance to do. We're getting a chance to see what happens when a large interacting system gets interrupted as it's going. So I'm nerding out so much. I'm having such a good time. I'm probably going a little bit over time. So let me pause there and just finish with that point. We'll jump to a couple questions.
Okay, thanks, Murray and Trevor. We do have a number of questions that have come in. And there's one about quantum annealing and AI, and it's kind of part 1 and part 2, so I'll read them both together. Can you please explain how quantum annealing can enhance AI? And the second part of it is, the research on using quantum annealing in AI is limited. There was a paper on QSVM, but its performance is inconsistent and does not always outperform classical methods. What are the possible ways to use quantum annealing to enhance AI with a guarantee that will outperform classical approaches?
Okay, so let me do can I maybe do the first part, Trevor? Is that all right?
Yeah, for sure.
So the way I would usually relate this to folks who are in the AI and ML space is think about these not as cards and not as spins, but as neurons that are firing and not firing. And when you're choosing how you're going to interconnect those, that basically determines like how your neural network is connected. So fast anneal is basically allowing us to probe, typically in machine learning, you set up a set of connections, you put some input data, and you look at how your neural network is going to react. And if it's not kind of showing sort of pattern detection, or if it's deviating from the kind of patterns you're seeing in your data, then you start tweaking the couplings between them. So here we've chosen a very simple set of couplings because it allows us to show it and explore it and intuitively see how it's going to react. This is a fast anneal feature, is allowing us to, we could connect this in a much more integrated kind of neural network sort of a way, and then we'd be able to catch it and pause it midway through and actually see what kind of states are coming out of the neural network. The other thing is that when you run it slowly and it starts interacting with its environment, the statistics start to change. So being able to run with fast anneal right in the long coherent regime allows you to get cleaner statistics of how this quantum neural network is behaving. And that's really useful for generative, like artificial intelligence models. And some examples of that would be like papers that have been published on like discrete variational autoencoders, where they use discrete neural networks in the latent space to learn patterns, which have been adapted to quantum variational autoencoders, where they use quantum neural networks in the latent space to detect patterns. Go ahead, Trevor.
Yeah, maybe at a high level, the core, machine learning and optimization are very intrinsically interwoven. So the whole idea in training a machine learning model is to optimize or minimize the distance between your data set and the output of your model. So optimization is at the core of modern machine learning architectures. Like Murray is saying, we're actually fairly excited about the coherent regime and the distributions coming out of the hardware, which I think are very just not tractable to produce with classical approaches. And so these distributions are rich, and I think could form the core of generative AI models. And so we have some research underway to investigate that, and we're very excited about that. But there's a whole host of optimization use cases that are very adjacent to machine learning that we're also very excited about. We have a module in Leap, a plugin called for feature selection, which really uses our quantum hybrid optimization solvers to do feature selection in the model training process.
Okay, and next question, we have a few people kind of asking about, can you list kind of existing examples where there are benefits for business that could be improved via fast anneal? So how would you kind of use this in the real world?
So maybe I'll tackle this one. We have a number of folks. So for instance, like Carlton Coughlin at Los Alamos was presenting at our Qubits conference in Boston in June about how they're studying and developing new materials, and they want to use this fast anneal feature so they can actually understand what's happening that determines the properties of materials when they're changing state. So if you're using it for applications and material simulation, those are ways that it can be used. When we're working on business applications, we're using like industrial software that's hybrid. It's using both classical compute and quantum compute for solving problems, in which case it's using the quantum computer. It's basically breaking pieces out of the problem where maybe things are kind of like stuck and frustrated together, and then asking the quantum computer, okay, how can you kind of rearrange these so that we get to a better overall state, which is actually a little bit like what we're showing here. So it plays a role as a heuristic in an industrial optimization solver that's basically helping it to like explore solutions when problems get really hard. So that's the relevance really there. And then, in machine learning, it's about, being able to use it, as Hadi was sort of mentioning, maybe not in a quantum support vector machine, but maybe as like a feature selection technique as part of a machine learning workflow, where we've seen some advantages, as well as potentially like a generative latent model in another sort of machine learning structure. So some ideas there.
Okay, thank you. We have one question about Bell's inequality. Someone says, I'm confused about the terminology because I thought that this was a theorem shown to be true for the Copenhagen interpretation of quantum physics.
Yeah, it's unfortunate because I think we went over time, so Trevor had to jump. But the Bell's inequality was about, when physicists were sort of saying, hey, quantum states can be in superpositions of states until you measure them and then they collapse. People were sort of saying, well, maybe it's not in a superposition, maybe it's just in one of the states and you don't know which one it's in. And so Bell came up with a theory, an experiment, where if you run the experiment, the systems are interacting when they're in the superposition, and that changes the statistics of what you see when you measure them. And so regardless of the interpretation of why you think quantum mechanics is doing what it's doing, whether it's like Copenhagen interpretation or other things, it's just about, setting up an experiment where you say, okay, these things are impacting. I can see the statistics have been changed, and this shouldn't be possible. It behaves the way classical systems behave. So it sort of was a key linchpin in sort of proving that quantum mechanics, the math of quantum mechanics actually accurately describes the way the world works. And here, we've got qubits that are loops of metal, and there's currents going counterclockwise or clockwise in them. So when they're in a superposition, there's a counterclockwise and a clockwise current running. If that was like a classical system, there would be no current, right? Counterclockwise and clockwise cancel each other out. And then there would be no magnetic field coupling this to any of the other qubits. So you basically wouldn't get this interaction between the qubits if they weren't, if they were classical and not quantum mechanical. So those are the ways in which this kind of affects the way that quantum processor runs. And as kind of shown in this curve as it's bending down, when you look at Kibble-Zerk theory, that slows down how quickly it can improve the solution quality. And that's how we can very easily tell quantum behavior, which is faster, from classical behavior.
Okay. Well, we have run over. This was intended to be 30 minutes, but we've had so many questions. And we have lots that we haven't gotten to. So I'm going to keep a copy of all these questions and send them to Murray and Trevor, and then we can respond to you via email. So sorry, we have to cut it off, and I hope you learned something. In the chat, by the way, there was a good article on Bell's inequality from Brian Lenihan, who some of you may know. So I put a link in there if you want to take a look at that. And other than that, thank you, Murray. Thank you, Trevor, who's already gone on to do more things. And thanks everyone for coming. Our next webinar is going to be at the end of September. Actually, Murray is going to come back, and it's going to be on quantum optimization on September 22nd, I believe is the date. So you'll get an email from us about that. So thanks very much, everyone, and hope to see you at a future webinar. Thanks, Murray.
Thanks.